That no problem. I don't know. I have not recorded, I think. But I'll see to you. Any problem is there? Okay, so today we are going to discuss very important aspects for the students who are doing the course on that inverter. So few things we need to understand actually. Say if you take the equivalent circuit of an inductor, okay, so how it will be? So here this is your inductor, and here one voltage source will be generated if you consider the initial current. So this is your Laplace transform of the source voltage in S domain, and this is Ls, where S is Laplace operator. You know all, hope. S is equal to j omega. This is the Laplace operator, and this voltage is L I0. This voltage is L I0 plus, basically the initial current which was flowing through it. So now say this terminal is positive and this is negative. Now you see this voltage basically opposing the source voltage. So eventually the current through the inductor will be initially very less, means it will suppress. But in case of capacitor, if you see, so say this is your capacitor, due to the initial voltage, so this will be this is Vc0 plus is the initial voltage of the capacitor by S, and this impedance is 1 by Cs, and this is your source voltage. Now you see this voltage will add up with the source voltage and it will increase the current through the circuit, okay. And you know the final and initial value theorem. So you should remember with this expression we can tell this is for capacitor, this is inductor, and this is my initial condition and this is my final condition. So initial condition means t tends to 0, and here t tends to infinity. So initially the capacitor, the inductor, it will work as a open circuit, and finally the inductor, it will work as a short circuit. But for an capacitor, initially it will work as a short circuit, and once it is fully charged, no current will flow, so it will work as a open circuit. So from this, why I am telling this, because when you will be making the inverter, so this is your DC source, and this DC source, it will be switched very high frequency. This DC will be switched, which will generate AC. This will go to load. So now you can understand, if there is a switching, on off is taking place, suddenly say current flow, we are breaking very high speed, we are making and breaking the current flow. So similarly, say one from a tank, if the water is flowing. So if that time very high speed you doing on off, so there will be a surge experienced by the source in the tank likewise. So to avoid that, you have to give some cushion, something to be given for compensation. So this capacitor will work as a surge compensator. Okay. So the whatever the current, sudden making and breaking of the current will be there, due to that whatever the fluctuation is taking place. So the capacitor will charge and discharge, and this capacitor will safeguard the DC source, which will make the DC bus very stable. If the DC bus is not stable, then it is not advisable to do the switching. So this capacitor is required. But here one problem is there. If I am simply connecting the capacitor across the DC source, then as I told initially, it will work as a short circuit. So once the DC source is on, very high current will flow through this. Okay. So to avoid that, one arrangement is to be done to avoid that. This is not applicable for very low power converter, but in high power it is required. In high power converter, this is required. What I will do here, I will introduce one resistor and then capacitor, and here I will make a two-way switch, and it is connected like this, and then my inverter. And what I will do, when at the initial condition, I will keep on continuously monitor the capacitor voltage. Okay, so at initially, when the charging will start, I will first close this pole. Okay. So what will happen? Due to this resistance, the current, the inrush current, which is supposed to be passed through the capacitor, this will be restricted. This will be restricted by the resistance. The resistance will oppose that high inrush current. And once the capacitor is slightly charged, so the polarity, here it will be positive and here it will be negative. So finally, the effective voltage will come down, and that time I will break this, and I will connect this, and I will connect this. So now the current, that charging current, the inrush current is maintained. This circuit is called pre-charging circuit. So you know, it's a simple RC circuit. You know how to solve the RC circuit by Laplace transform or normal time domain also, you know. So using that you can find out the peak to restrict the current. You know what is the maximum current to be can take care by the circuit, and based on that you can select your resistance. Okay, so you have to design your pre-charging capacitor and this mechanism, your inverter also, whatever inverter you are going to do. So this part you will be taking from your lab, regulated power supply, and this part you have to make. That calculation and all you can try, and if you are not able to complete, then you can ask, I will help you how to calculate. It's very simple. It's simple RC circuit. you know what should be the maximum current, the source, this source having a voltage and current rating. So definitely your resistance should be selected such a way that during the charging current which will flow through the circuit should not exceed this value. That's all. So for that, how much the resistance is to be added? Simply by Ohm's law, by solving the Laplace equation, you can find it out. Okay. Now another thing is there. You see, basically in inverter, what is going to happen? This is the DC source, and here the two switches will be there, or here one more set of switch for H bridge, and this is my load, and it is grounded. These two switch, say 1 and 2, these two switch will be switched in a particular fashion so that we will get perfect sine wave. That I will tell you later. What is that? It is nothing but the volt second balance. You already learned the Fourier transform or Fourier series. So that is basically implementation of that only, nothing else. So you see, what you are learning, what you have already learned, then where it is to be applied, I am trying to give that flavor, because you may feel that I studied Fourier series, Fourier transform, Laplace transform, it is where I will apply. Normally I also, when studied, I have that doubt. So now I understand that after this much of industrial experience, I understand it is very much important. Okay, so that only I am trying to tell you. People who will be joining in software companies, they will be working in different fields, they know they don't need all these things, but still I am telling you. So now you see, if for any instant these two switches are close together, what will happen? Just one minute. Okay, so what so what I was telling, if any instant, if these two switches are on together, what will happen? The DC source, it will get shorted through this path, and very high inrush current will flow, which may destroy the PN junction of these switches. So while you are designing the inverter, you are writing the code, definitely you should, it is to be taken care that for any instant these two switches should not on together. Okay, so even though we know theoretically that when I am giving the on command, immediately the switch is on, and when off, immediately it is off. But in actual case, this is not happening. When you are giving the pulse, rather than getting on very sharply, it will on like this. It will take some time. And when you are initiating the off command, the triggering pulse, when it is getting off, rather than sharply falling it will be like this. So this period it is called the on time, and this period it is called the off time. Okay, so when the other switch is getting on, so definitely what should be there, see, during this period, the switch, the other switch, so what I mean to say, this is your actual microcontroller pulse, for example, and actually what is happening, it is happening like this and like this. So similarly it is like this and it is like this. So the complementary, the bottom switch get on only in this instant, okay, and it is off like this, okay, and so on, okay. Just okay, actually you see I am busy with several activities, so that's why whenever I am trying to teach you, so that is my target. So that's why without informing, whenever I am getting time, I am trying to sit with you. So this is the thing. So so these pulses should be like this, okay. So from this discussion we understood that for this period, and here it is this period, always the complementary switch should be off, This time is called dead time. During this period, the complementary switch should be, means in this period there should be a gap. That means no current will flow during this duration. So this is called the dead time. So whenever we will be designing the inverter, even though it is half bridge or full bridge, basically we will be doing it through complementary switching by generating the PWM. So while we will be generating the PWM, definitely we should be taken care about this dead time. And this dead time, this T on and T off, T on and T off should be, it is defined in the data sheet, okay. So these things, how to generate the dead time, by seeing the data sheet, these things we will learn in the next class. I'll tell you how to, from the seeing the data sheet, by PWM, what are the parameters are to be considered to generate the exact dead time, okay. So I am stopping here today because one professor is coming online. She is asking some